So this video, we're talking about two theorems of polynomials. One is called the remainder theorem, and the other is the factor theorem, which we're going to get to in a little bit, so don't worry if we don't get to it right now. So the remainder theorem, the best way to describe the remainder theorem is to perform this synthetic division, because in division is where we find remainders. Okay, so let's talk about how we do synthetic division. First of all, I hope you notice that this term is out of sequence. Okay, before we want to do any synthetic division, we need to have it in the correct standard order. So now that it's in the correct order, right, synthetic division involves making this upside down division house. Maybe that's not its specific name, but this is how we perform it. Okay, so synthetic division is only involving the coefficients of your polynomial. So first we write them down on the top half of this little house here, -3, -2, 2, and 1. And because it's in order, if ever we are missing a power of x, you have to put a 0 in for that missing power. Okay, there has to be a placeholder for every single exponent in your problem. Okay, now we look at your divisor. So we are dividing this by x minus 1. The polynomial we're dividing by x minus 1. So to figure out what number we're dividing by, we solve that linear divisor. Okay, and this only works when we have linear divisors. So if we ever have an x squared out here or an x cubed, then this method won't work. So as long as that's an x plus or an x minus or even a 2x, right, it just has to be a linear having a single power of x. We take that number and we put it in front right there. Okay, so this is the procedure that we do every time we have synthetic division. Okay, so now we do the recipe. The first step is dropping down this first number. And then we multiply the 1 on the outside times this number, and we put it here in the next column. We multiply 1 times -3 and put it in the next column. And the columns we always add. So -2 plus -3 is -5. And now I repeat the steps all over again. I take the number on the outside and I multiply it by the next bottom number and I put it in the new column. 1 times -5 is -5. And now I add 2 plus -5 and get -3. And I continue doing this process until I have multiplied and I no longer have any numbers anymore. Positive 1 times -3 is -3. And when I add these things together, I get a final answer of -2. And for my theorem, this is the important number. This number that is last here on the row, this is your remainder. Okay, this -2 is the remainder that you get when we do this division problem. Okay, and we move over, this is the number, this is your x term, and this is your x squared term. Okay, so when we do this division, right, the quotient, or the quotient is the answer that you get when you divide would be -3x squared minus 5x minus 3. Okay, so we can look at your numbers, right? Look at these things down here. These become coefficients of another polynomial, right? The polynomial that you get when you do this division up here, right? You divide a poly by a poly, and the answer is a poly. So it's given to you by all the numbers on the bottom. Okay, and we'll use that in a minute, just not just yet. Okay, so let's practice that again with this problem. Okay, so notice we are missing an x cubed term. So we're going to have a 0 in that space. We don't have an x cubed, but we have to have a place for it. So there's a 0 that represents how many x cubes we have. And now we find the number on the outside by solving your divisor. X plus 2 equals 0. So that number is -2. And now we perform your synthetic division. First, we drop down the 3. Multiply it by -2, and it goes here. And then we add these together, and we get -6. And then you multiply it by -2, and we get +12. And then we add, and we get 13. And you multiply it by -2, and that's -26. And we add, and that's -29. Multiply by -2, that's 58, +58. We add, and we get 61. So we have a remainder of 61 when we divide 3x to the 4th plus x squared minus 3x plus 3 by x plus 2. Okay, and our last example of synthetic division. Okay, so let's set this up. So we drop down the 2. 1/2 times 2 is 1. 1 plus 1 is 2. 1/2 times 2 is 1. -13 plus 1 is -12. 1/2 times -12 is -6. -6 plus 6 is 0. So here, this one has a remainder of 0. Now, in the end of this video, that's going to be an important thing, is having a remainder of 0. But for us right now, that's just a cute little anomaly. Okay, because we're just trying to find the remainders, performing synthetic division to find the remainders. Okay, because now we want to make a connection between what the remainder theorem says. So there's a lot of different things to do, right? There are no fewer than 5 of these examples. Okay, 5 examples. So we might do a couple of them, we might do 2 or 3, but we're first going to start with 1. So we're going to see what happens when I plug 1 into my equation, right? So P of 1 means plug 1 into all of these equations and evaluate, and let's see what we get. So we have a y value of -1 when I have an x value of +1. So P of 1 equals -1. Good to know. Okay, so now let's come over here and do this synthetic division. Okay, so we're dividing by x minus 1, which means we are using +1 to synthetically divide our polynomial. So the remainder, when I use synthetic division, is -1, and the y value, when I plugged in +1, was also -1. Maybe we're suspicious. Let's try it again for this next example. We're going to figure out what the value of P of 2 is. So we evaluate P of 2, and we figure out that the y value, when x is 2, from our function we're calling P, is going to be the number 11. Okay, so P of 2 equals 11. Now let's come over here and do synthetic division. Okay, equals 0 with x equals 2 on the outside of our house. And let's see what we get. And we notice that the remainder, when we use synthetic division, is 11. Okay, so we could do examples until the cows come home, but I think you can probably guess what's going to happen. And what's going to happen is, when you substitute that in, that's the same as if we'd got the remainder from your long division. Okay, and this is basically what the remainder theorem says. In fact, it's exactly what the remainder theorem says. That you can divide by the factor, right, using synthetic division, and the remainder will be the same as if you were to be evaluating it for that 0, right? So this number here is the same as that number there, right? Your your synthetic division value is the same x as what we are plugging into your equation. So that's what we're going to write over on the other page about the remainder theorem. So here's a screenshot from Google AI. Told us that, of course, also known as the polynomial remainder theorem, because we're talking about polynomials, or Bézout, right, the French guy. So here's what we have. The polynomial is divided by some linear fraction. It's the same as plugging that into the formula. Okay, so in essence, that's what it means, is that we can calculate the remainder of a polynomial without having to perform long division, right? Because nobody likes doing long division. So in essence, that the remainder is the same as the y value when evaluating. So that's what I need you to remember, that the remainder from synthetic division is the same as evaluating at that x value. Okay, the remainder from synthetic division is the same as evaluating. Okay, sometimes one is faster than the other, which is why you might prefer, actually you never prefer to do that. You probably will just ask Google or chat or somebody else to do it for you. Right? Very, very efficient method. So let's look at some cute little math problems that deal with remainders and synthetically division. So it says, what value of k, so we have an equation that has k in it. For what value of k will have a remainder of 8, so we want to get some specific answer when it's divided by this linear divisor. Okay, so we want to have a specific remainder. What value of k will make that happen? Okay, so we're going to start by doing synthetic division. So here is your polynomial that we're going to synthetically divide. Right, we make our upside down house. We look at the coefficients. -2, -2. K is the coefficient of x, and -2. Okay, and now we have to divide it by something, so we solve over here. X plus 2 equals 0, so x equals -2. Now remember what we want. We want the remainder, so whatever's going to be right here, right, this is where the remainder happens. We want this remainder to be equal to 8. So we're probably going to have some type of a mathematical equation there that we're going to have to solve. Okay, so let's just see how this goes. Synthetic division, we drop down the -2. We multiply -2 times -2 is +4, and we add. -2 plus 4 is +2. Multiply by -2, and I get -4. Right, and now I add. K plus -4 is an equation, k minus 4. So here we have begun our equation, right? We're adding. You can't add a letter and a number, so you write them down as an expression. And now we multiply it by -2. That means I have to distribute. So -2 times k is -2k. -2 times -4 is +8. So now I am adding a number to an expression. I'm going to combine my like terms. What is -2 plus 8 is a +6. So I have the equation -2 plus 6, which is the remainder. That needs to equal 8. Okay, so I have just made an equation that I can solve for k. So if I really wanted to have a remainder of 8, right, for whatever reason, I'm not quite sure why I would want to have a remainder of 8, that means k has to be -1. The coefficient of your x term would be -1 if we were supposed to be getting a remainder of 8. Okay, just some cute little math there, little algebraic equation. Okay, let's try it again for this bottom one to see if we can solidify that mathematical knowledge. So here we want to have a remainder of 4. So when we do our synthetic division, we need to get 4 as the remainder. Right, so we're going to set up our synthetic division. Positive 3 is the number we're going to be dividing by, and we're going to set whatever your remainder is, whatever equation we get for there, we're going to set that equal to 4. Okay, let's see what we get. So I get a remainder of 9k plus 76. Okay, and I want that number to be equal to 4, so now I have this equation that I can solve for k. So I subtract 76 from both sides, and then divide both sides by 9, and k would have to equal negative 8. If k were negative 8 in my original equation up here, and I did synthetic division, I would get a remainder of 4. Okay, for whatever reason, it's just some good algebra practice, I guess, plus a little knowledge about remainders. Okay, let's move on to our next important thing, the remainder theorem. Sorry, not remainder theorem, but factor theorem. That's what we're looking at next, the factor theorem. Okay, so the factor theorem is saying that if this linear thing is a factor of a function if. So here's the if. If, when you do synthetic division, you get a remainder of 0. So if you get a remainder of 0, then your linear guy that began with, your linear divisor, is a factor. So we're going to do synthetic division to see if we get a 0 as the remainder. If we do, that means that is a factor of your polynomial. And if you don't, then it's not a factor of your polynomial. Okay, so let's check this one out and see, is 2x plus 1 a factor of this polynomial? So let's do the synthetic division. So we set up your division. We look at only the coefficients of your polynomial, and then you solve your linear factor, potential factor, to get negative 1/2. Okay, we always solve your linear divisor to see what you get out here. So let's do synthetic division and focus on the remainder. Okay, focus on the remainder. And looky there. When we do synthetic division with negative 1/2, I get 0 as my remainder. Okay, so that means yes, 2x plus 1 is in fact a factor of this polynomial. Okay, and what's the graphical interpretation? That means negative 1/2 is where the graph crosses the x-axis. Right? This is a 0 for your polynomial. This is a root. This is a solution. This is your x-intercept. Okay, all of those things are true. If we have 2x plus 1 as a factor, then negative 1/2 is a 0. Okay, wonderful. That's what the factor theorem says. We want to get a remainder of 0. So let's look at number 3, because this is how we're going to do all the stuff basically going forward. Okay, so we have x cubed minus 13x plus 12, and we're going to find the zeros of that function. Okay, so we're going to first start by doing what they say, divide it by x minus 3. Okay, we're going to use synthetic division to do this division. Okay, so we have 0x squareds, so we have a 0 in that spot. And we're going to use positive 3 as your outside number there for your synthetic division. Okay, so let's see what we get when we synthetically divide. So pretty amazing. We get 0 as a remainder. That means that x minus 3 was in fact a factor, and positive 3 is a 0. So it says factor the quotient. Well, what is the quotient? The quotient is your answer right here. Okay, so that doesn't look much like a quotient, does it? So if this is your remainder term, that means this is your number term, this is your x term, and this is your x squared term. So my quotient is x squared plus 3x minus 4, okay, which is going to be a factorable quadratic. What numbers multiply to give you negative 4 and add to give positive 3? Those numbers are positive 4 and negative 1, of course. So then we can factor your quadratic is x plus 4 and x minus 1, which means your other two answers are negative 4 and positive 1. Okay, so we have three solutions to this. We have positive 3, right? We got that from your synthetic division. We got a quadratic as your quotient, which we factored, and then we solved those two factors to get your other two solutions. Okay, so part B and part C, right, are doing the same thing, but notice here we have that one, and then we have x plus 4. So it's giving us all of your zeros that we're going to be factoring. Okay? Factor theorem says that if you get a zero remainder, then that linear is your factor. And that is all for today. Goodbye.